last class you have seen that entropy is proportional to the number of microstates, and the reason behind the increase of entropy with time was discussed as that entropy is nothing but options. When you have more options, you have more entropy. So, in order to show that, I have shown that movie of water in which you could see that every time instant the number of the configurations of the particles were changing. So, therefore, at every instant of time a new microstates were being generated. Now, there for a very complicated systems like water in a glass, the string of numbers constituting their positions and momentum can be thought of as a microstate. Let us say if you have one particle, one water molecule, then it will have 3 atoms, therefore 9 positions and therefore 9 different momentum. So, this 18 number will constitute one microstate. If you change any of these 18 numbers, then a new microstate will be generated. So, today we are going to talk about much simpler system, and then we will come back to this complicated water systems maybe later on. Water system is also complicated because there are interactions between the water which will also change the possibility of certain microstate being there or not being there. So, in order to understand what is a microstate, we will discuss some simpler problems. Before that also we will just remind you that we have also discussed about little bit of probability, and we discussed about the AND probability, OR probability and the combination of them. We showed you that when the number is large, then only the probability values are coming to be the desired value. For example, when you toss a coin it becomes 0.5 only when you toss many number of times, and the distributions of probability mass functions for 2 die throw becomes perfect only when you do very high number. In our case we have shown 10,000 trials, 100,000 trials actually gave a right symmetric distributions at the sum equal to 7. So, today we are going to talk about distributions and microstate. So, by distribution what we mean is that imagine that die throw. So, there we could see that there were 11 different possibilities, some as 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So, there were these 11 possibilities, and by distribution it means that out of 10,000 or 100,000 trials, each of these possibilities occurred some number of times, and which means that our sum of 2 dice got distributed in these numbers between 2 and 12. So, when you talk about distribution, and then each distribution had some possibility, some probability. So, here we talk about much simpler thing. When you talk about cards, we know what distribution means, right. So, typically if you know about playing a card, then typically there are games called bridge where there are 52 cards and you distribute 13 to each of them, and so that is called distribution, right. So, let us say there are 4 players, 1, 2, 3 and 4. I distribute 4 cards in 4 players. Make it simpler, and let us say there are only 2 players. So, I distribute 1 card, 2 card, another card, another card. So, I distribute my 4 cards into 2 different people, 2 hands or 2 sets. Now, each hand has some cards. For example, here you could see that there is 1 heart and 1 diamond. By the way, these all 4 cards are aces. So, they are all A, as you can see A here, and there are only 4 such cards, 1 from diamond, 1 from heart and 1 from club and 1 from spade. They are all distinguishable cards because I know aces of heart and aces of clubs, aces of diamond, aces of spade. I know these 4 cards, distinguishable cards, but forget about that, they are hearts, spades, clubs and diamonds. Look at their colors. What do we see? In one hand I saw 2 red, another hand I see 2 black. Now, this is just one occurrences of my distribution. I can distribute again. I shuffle it and then let me distribute it again. What do I see? I see one black and one red, and I see in the other hand of course one black and one red. Now, what do you think, whether this is a better possibility or the other one in which one hand had black card and another hand had red card is a possibility, higher possibility. So, which one will be more probable? So, in order to understand that, let us see that all possible combinations of these 4 cards distributed among 2 hands. So, here again as you can see they are all aces, just think about that, they are all aces, I have not specified that. And now I am going to distribute them in the hand 1 and hand 2, and you can see I distribute heart and diamond to hand 1 and spade and club to hand 2 in one of the distribution once when I give it, and then I can also give heart and diamond and club and spade, another possibility. And if I go on like that, then as you can see there are 24 possible distribution of this 4 cards into 2 hands. The reason is that why there is 24 possibilities, because there are 4 different cards: hearts, spade, club and diamond. Now, when you give the first card I can pick any of the 4 possibilities. This first card I do not know, I am not looking at it, therefore, it can be I can choose and pick, and I can actually take any of the 4. Once I take any of the 4, I have then I am left with 3 more cards. Second one I can take any of the 3. So, 4 into 3 is 12. Out of the last 2 cards I can take any of the 2, 4 into 3 into 2, and then I am left with only one choice into 1. So, the number of possibilities as you can see is 4 into 3 into 2 into 1 is equal to 24, and that 24 is actually given here, that 24 possibilities. So, now I say that okay, I have these 24 possible ways of giving this card, but I want to summarize this into 2 main distributions. In one distribution I say that one hand has both red card, which we saw the first time. How many such occurrences are there? Let us see where one hand red card and another hand black card, and hands are independent, that means it is okay that if the first guy gets both the red or the second guy gets both the red. So, let us see such occurrences. This is 1, 2 and then 3, 4 and then 5, 6, 7 and 8. There are 8 possible situations where one hand gets one particular color red or black, the other hand gets another particular color red or black. There are 8 such situations. So, if that is the case, we can say that the number of microstates corresponding to a particular hand getting one particular color is only 8. Total number of microstates again is 24. Therefore, probabilities of this particular distribution, which we call distribution A, is 8 by 24 or basically 1 by 3. Now, let us say I talk about distribution B. I say that each hand has one black and one red card. So, mixed card. What is the probability that you will get a mixed card? In that case, all other things, all other than the 8, they are all mixed. So, there are 16 possible mixed situations are there, and then the probability of that distribution will be 16 by 24 or 2 by 3. So, without doing or distributing this using the probability, we can say that when you distribute the card, these 4 cards, then the probability that you will get a mixed color card is much higher, is higher, it's actually double than the probability that you get same colored cards even without doing that. But remember, you may get 2 red cards or may get 2 black cards in one occurrences. However, when you do several times, multiple times, then it will be more probable that you will get a mixed card. So microstates are, again we can say that all possible arrangements. What are the possibilities of distributing these 4 cards is what we can think of as microstates. Remember, if 2 distributions are identical or 2 arrangements are identical, then we will count only one. So, we will not count them twice. For example, when you define that there are black cards and red cards, 2 red or 2 black, then we already define the situations and we count in that all possible variations. So, what do you mean by then the distribution? So, distribution is that when you distribute either a card or particle or something into 2 or more people. So, let us say distribute cards to people, that is a distribution, or distribute particles to different energy levels, that is a distribution. So, distribution literally means that you are giving it, dividing it to certain parts, and then number of microstates will be how many possible ways you can do that for one such distribution. So, for when you have one hand getting same color, that is a distribution and number of possibilities is 8. One hand getting mixed colored is a distribution and the number of possibilities is 16. So, that is what we distinguish between distribution and microstate. Let us do more about that. So, instead of counting all possible distributions like we showed, we actually enumerated all 24 and we actually showed you that there are 8 possible situations in which one hand gets black card and another hand gets completely red card. We can use probability and calculate the same thing. So, when I give the first card to somebody, what is the probability that I am giving a red card? 2 by 4, because there are 2 red cards out of 4 cards. So, the probability that the first guy gets a red is 2 by 4. Probability that the second card is red, because there is only one more red card left, right, out of these 3 cards, it should be 1 by 3. Probability that the third card being black, now I have only 2 cards left and I know they are both black, right. So, probability that the third card is black is 2 by 2 and probability that the fourth card is black is 1 by 1, because there is only one card left and that is also black. So, the total probability, now see we are invoking the AND probability situation here, that first card being red and the second card being red and the third card being black and the fourth card being black. So, I am multiplying all of that and I am getting 1 by 6. But that is not the only situations in which one hand gets red and another hand gets black, right, because there is a situation in which I can, instead of giving that second guy red card, I can give them black card. So, I also have to count that the first probability the first card being black, probability the second card being black, probability the third card being red and fourth card being red. So, in that situation that will be same as 1 by 6, right. So, I am denoting that probability as RRBB, that means first card red, second card red, third card black, fourth card black. This will make it in 2 hands RR and BB, and in the second case first card black, second card black, third card red, fourth card red, and I am getting another possibility. You see here that I am not distinguishing between 2 hands. I am not saying that hand 1 has to get red and hand 2 has to get black, that I am not saying here. I am saying any of the hands should get any of the color, but same color, and that is why I need an OR probability, and that OR probability, as you know, adds, and because of that my total probability that one hand gets one color, the other hand gets the other color is 1 by 3. You see, now without enumerating, if instead of 4 cards if I had 20 cards, or 20 different colors. Should I be enumerating all of them, writing all of them down? No, I have to use the probability to estimate that what will be the number of possible microstates and what will be the probability of that distribution. Why I am talking about probability of a distribution? You have to distinguish between distribution and its probability. So, we will see later on that there are many possible ways of doing performing a distribution, and in that there is one distribution which will be maximum probable, and you will see that the situation will go towards those probability. What I mean by that is that if you keep on shuffling the card, you will see more and more a mixed color card, one hand is getting a mixed color card, that is going towards a more probable situation. Here there are only two possible distributions. So, that is why you go from one to the other, not like many. So, but wherever there will be many possible distributions there, and there will see that one possible distribution will be maximum. So, now let us do the PB the same way. First card black, second card first card red, second card has to be black for the hand 1, and then for the hand 2 it should be red and black, that is one possibility, right. In that case hand 1 and hand 2 will get mixed color. Hand 1 and hand 2 will get mixed color when first card red, second card black, third card black and fourth card red. Also another situation will happen when first card black, second card red, third card red and black. So, basically if I do it in a short notation, it is RB RB or RB BR or BR RB and BR BR. All possible situations will give that. Each of them has 1/6 possibilities. When you add them up, you will get 4/6 or 2/3. So, mixed color card, as you can see, will have double probability than the same colored card. So, now we know that what distribution is, how you are using probability to estimate the probability of one particular distribution. Why it is important? You will come to know soon enough. Why we are talking about cards? Because it is simple enough, we can understand from this and then we can apply to a realistic situations later on. So, scientists always try to think from a very simplistic point of view, so that they understand what happens in simple things. Once they understand that completely, then only they apply to a more complicated systems like a glass of water. Believe me, it is extremely complicated. Even the theories of that will not be even discussed in this particular course, and sometimes even later courses. We still deal with very simple situations and try to understand that. Only very complicated situations we will try to deal with systems like water. So, now the situations that I talked about, distributing cards in hands, the similar situations or most common probabilistic situations is distribution of R balls in n boxes. You can say in n boxes. This particular problem, R ball in n boxes, is so common that it can be used in many different situations. It can be mapped or it can be thought of or projected in many different situations, including that of our current discussions of number of microstates, of particles and chemical systems and things like that. I will give you some example. So, as I said, many probability calculations are equivalent to the above descriptions of placing R ball in n boxes. For example, we talked about dice throw, right. Dice throw is what? There are all 6 possibilities, right, for one particular die. When I throw the second time, what do you say? Again 6 possibilities, right. So, you can think of the possible outcome of throwing R dice, let us say, is corresponding to placing R ball in n equal to 6 boxes. Why that is why we are saying that? For example, if you have n equal to 6 boxes, means the box are distinguishable. That means, if I get 1 by throwing a dice, it means that I am putting a ball in box number 1. If I get 5 by throwing a dice, I will say that I am putting a ball in box number 5, and my balls are distinguishable because I throw the first dice, I throw the second dice. So, my dices are distinguishable because I have first die, I have second dice, I have third dice, and the boxes are denoting what is the outcome of throwing a die. So, in a way you are looking at a situations of placing R distinguishable particles. Why distinguishable? Because first dice, second dice, third dice we know, in 6 distinguishable boxes. Why distinguishable boxes? Because outcomes are distinguishable. So, that means if I throw 2 dice for example. So, if I throw 2 dice, then my R equal to 2 and N equal to 6. What are the possibilities that I can get? I can get any of the 6, I can put in any of the 6 boxes. So, the outcome is 6. Second time also I have the outcome of 6. So, when I throw 2 die, it is 6 into 6 or 6 to the power 2. If I throw it 3 times, it is this 6 to the power 3. If I throw it how many times? R dice, right? It will be 6 to the power R. So, in general, my formula of placing R distinguishable ball in n boxes is n to the power R, because I will come back to that more on this. Another situation is that coin toss. Now, can you tell me that how the coin toss can be associated with putting ball in the boxes? So, coin tosses has 2 outcomes, head or tail. So, I can say that one box is head, another box is tail, and my first coin is a one ball, my second coin is another ball, my third coin is another ball. So, it is putting R balls into 2 boxes. So, first ball can be in any of the 2 boxes. So, 2 possibility. Second ball can be any of the 2 boxes. So, 2 possibilities. So, like that, if I have R ball, it will be 2 to the power R possibilities. Birthdays, another example, that the possible configurations of birthdays of R people. So, first person can have birthday in any of 365 days. Second person can have birthdays in any of 365 days. Third person can have. So, here n is 365. So, boxes are 365 boxes. You can number them according to the number of the days, and people are like balls. So, you are putting them on the first day on the calendar. Let us say you have a calendar, and my birthday is, let us say for example 8th August. So, I will be on that day, I will be standing on that day, somebody else will be standing on some other day. So, you can imagine that birthdays are nothing but putting distinguishable balls like you and me into distinguishable boxes like the particular day of the calendar. Another example, energy distribution, a certain n units of energy distributed among R particles, that is a possibility, right. So, you can say that in this case, of course, the energies are not distinguishable in some sense, but you can say we are talking about balls and boxes. So, we can say that we are putting some definitive energy values, either epsilon or 2 epsilon or 3 epsilon into R particles. So, let us first start with very simple system. So, we have seen that by working on the distinguishable working on this placing balls in boxes, we can understand different situations related to creating new microstates, including the talking about the cards. For example, we had like 4 cards, right. So, that 4 cards, and there are 4 distinct possibilities: heart, spade, club and diamond. So, you can say that there are 4 possibilities, and in that 4 possibilities, if you have multiple number of cards, for example 52 cards, then you will actually place them accordingly, right. Anyway, so let us start with very simple system. Distribute one ball in one box. One ball in one box. How can you do that? You have only one ball and one box. How many possibilities can you imagine? One ball and one box, just one possibilities. So, I will say Number of possibilities we are denoting by W. Remember, we said that W is number of microstates. We can say number of possibilities as well. And since microstate is equivalent to entropy, then entropy is equivalent to possibility or options. That is what we discussed, right. So, let us call that as W, and that can be only one. We can no other way. If I have to place it, I have to place it. But let us say I have to place it, okay. I may not choose to place it, that is another possibility though. Distribute 2 balls in one box. Cell and box are actually the same thing, but just specifying box. So, this is our box, right. This is our typical box, and this is the ball that we are talking about, okay. 2 balls in one box. How many ways you can do that? I have to place 2 balls, only one. I do not see any other way. So, box is important. So, you remember, say imagine what is the formula we got? Number of boxes to the power balls, is not it? So, in this case it is 1 to the power 1 equal to 1, in this case it is 1 to the power 2 is also 1. Now, let us go to little bit more complicated situation. 1 ball in 2 boxes. So, I have these 2 boxes and I have 1 ball. I can place it either on the left ball or on the right ball. I can place it on the left box or on the right box. So, I am getting W equal to 2. So, here what is the situation? Box to the power ball, right. Box is 2, ball is 1 is equal to 2. N to the power R is the situations where balls and boxes are both distinguishable. That is why I drew the boxes in a distinguishable fashion. Distribute 2 balls in 2 boxes, 2 balls in 2 boxes. You see what will be the answer, right. 2 balls, 2 boxes, it should be 4, is not it. Let us see, 2 balls on the left box, 2 balls on the right box, 2 balls on individual boxes and 2 balls again on the individual boxes, but swapped. So, you see, because my boxes are distinguishable, I can distinguish between this and this, otherwise I could not have distinguished. If my boxes were identical, then this will mean the same thing, but here boxes are also distinguishable, and therefore, we can see that okay, my green ball is in a bigger box and here my green ball is in a smaller box. There must be 2 different configurations, not one. So, here both the balls and the boxes are distinguishable, otherwise we will not get all the 4 possibilities. So, now we are going to go to a little bit more complex situations. Distribution of 3 distinguishable balls in 3 distinguishable boxes. So, here are 3 distinguishable balls. We will make it distinguishable. Let us make it red. Now, we have 3 distinguishable balls and I need to put it in 3 distinguishable boxes. You know the value, right, it will be n to the power r, 3 to the power 3 equal to 27. Let us see all those 27 possibilities. I can call them also as A, B and C. Okay. So, here as you can see, all A, B, C are put in the first box and nothing on the second and third box. Here all A, B, C are put in the second box, nothing on the first or third. Here all A, B, C's are put on the third box, nothing on the first or second, and like that we get 18 and then finally all 27 possibilities. Because I did not have enough space here, I could not really draw the boxes and balls and show the configuration. So, this is a shorthand notations by which I am showing all possible combinations of putting 3 distinguishable balls in 3 distinguishable boxes. How the boxes are distinguished? The first one, the first box is, let us say you can call it 1, box number 1, second is box number 2 and third is box number 3. Once you distinguish the box, then you can automatically get that this will be the possibilities. And as you see that here also I have number of n equal to 3 and r equal to 3, and therefore, number of possibilities is as we saw n to the power r or 3 to the power 3 or 27. Now, I can think of that as this way: place the first ball in any of the boxes. So, let us say I have 3 boxes, right? Box number 1, box number 2 and box number 3. I can pick up any of the ABCs and put on the first box, and then I can take it out. It is called placement with replacement, and then place the second ball and the third ball. So, here place the first ball in any of the 3 boxes, then then you can take it out, and then place the second ball in any of this thing and take it out, and place the third ball in any of the boxes and take it out. So, this is called placement with replacement, because otherwise once you place your first ball, you will be left with only 2 more, right. But distribution with replacement allows us to have 3 balls back again. So, this particular situations of distinguishable balls in distinguishable boxes is placement with replacement. So, this is called with replacement. Otherwise, if you put A, you no longer have A, you have only B and C. But in these situations, I put A and then take it back A, I still have ABC, then I can choose any of that, again I can choose A and put it back, again I can choose A and put it back. So, this is the situation in which we call that placement with replacement, and there is some situations where we can do without replacement also, we are coming to that. So, therefore, if you have R ball in n boxes, then the first ball can be any of the n boxes n ways, the second ball can be any of the n boxes, so n into n, the third ball in any of the n boxes. Continuing that, I have R ball that can be placed in n into n like R terms, and it will be n to the power r, as we explained before. Now, as I said already, that drawing n distinguishable balls r times with replacement gives the same result. So, let us say you have 3 colored ball in a box. Now, you want to pick up one of them, there are 3 ways to do that, and you put it back again. Again you pick up, again 3 ways, you put it back again, again you pick up. So, every time you pick up, you have 3 choices. So, because you are replacing the ball, right. So, it is called replacement distinguishable ball with picking up r times with replacement. So, this result with replacement is very important, because you are replacing the ball back again, you are getting the same result. Okay. Now, we will see if you do not replace it, what would be the situation. That situation is called permutation.